is the one domain we are looking into. And then transformers and their inductances can be also visualized. Sensors, so here you can see it's a um, speed sensor that is visualizing the how it's to measure the optimum distance between the sensor and the moving part, to understand, like, which will give the most accurate value. Here is a three pole actuator, and that's, you can understand the forces, the electric magnetic flux density, the current density. All these quantities can be visualized to understand the impact of these quantities, and what sort of force will be experienced, so you know what housing you might require, or what sort of fastening of this actuator is required. Insulation and electric field, so lightning is something that we usually simulate a lot, for understanding the effect of lightning on safety devices and on conductors and all of that. Then we have induction heating, which is an industrial application where you understand the mu r changes, or the hardening of a billet in the example. Wireless charging, which is which is up and coming these days. Everything from mobiles to cars are being, like, tried to wirelessly charge. So there's something called a coupling factor. You want to understand the phase difference between the two, primary and secondary, so you can definitely simulate that as well. Electromagnetic compatibility at low frequency for so well, it's a concept that is used by, what we say, for extensive multi-body systems with multiple systems uh, inside the, for example, a vehicle. There are multiple systems, so you have to make sure they do not interact with each other. So electromagnetic compatibility, this can also be done. Cables, may be it underwater, overhead, or buried, or any sort of cables, they need to be simulated and understood, so the coupling inductance, the influence of one cable on the other. In case there is an earth face ground fault or a line to line fault, will the insulation break down? Will you need to, like, there are so many fault conditions and so many parameters that have to be understood of a cable. Ship magnetic signature is again a defense application, where you understand there are different, again, like a car, there are different systems in a ship, their effect on the hull, their effect on the direction of the ship. So the effect of the entire globe's north south magnetic signature on the ship. So all these make a big difference. So designing of degaussing coils and all of these advanced components require a better understanding of the electromagnetic parameters of the ship. And then come bus bar systems. So there are parasitic capacitances and inductances. And in case there is a fault, the heat, the thermal characteristics of this, all these need to be simulated. And definitely power modules, at a smaller component level, this thing can be simulated in flux as well. So, like I said before, motors and generators, we have multiple, dimensions to simulate motors and generators. You can either simulate it in 2D, 3D, or skew, and I will get into what is skew in the coming slides. You can couple it with an electric circuit or rotating motion. So this is, like, flux allows you to couple your motor to an electric circuit, so you can pump current or you can pump voltage, and you can see the reaction of your motor in different this thing, and you can even apply a rotating motion. So say you're in a generating mode where you're simulating a generator, the same can be done. You can see the advanced analysis of losses, even graphically. Apart from visualizing it on a graph, you can even visualize it on the entire geometry, in which part you're having the most amount of losses. Is there any way to avoid it by making any geometrical changes? All these can be definitely simulated and understood. Demagnetization of magnets, which is a very important concept that is being tried on today because of the rise of electric vehicles. It is important we understand the demagnetization of these magnets. The same can be simulated for influx. The efficiency maps. So when we say efficiency maps, we all know that the motor has a motor generator, or an electric rotating machine has four generating modes. So you can run these, I mean, four modes per se, not generating modes, four modes per se. You can generate the efficiency maps for all four regions, in the sense the speed torque graphs with their efficiency for all operating points of the entire motor. So basically the entire characteristics of the motor or generator. You can go ahead and couple this with system level tools, like for 1D simulation. So I think we are all familiar with Simulink. So for component level simulation or system level simulation, you can couple it with Flux, where you are your motor is being solved in real time and being given, the inputs that you're given in Simulink. So that can also be done. And then multi-physics optimization. So multi-physics optimization is something that, requires an in-depth understanding, which I will get into in the next coming slides. Coming to power transformers, like I like just like motors, even power transformers have a lot of quantities and a lot of forces and different parameters that you would wish to visualize depending on what your application is. So you can model, so we do not have a size constraint in Flux. You can model any size as long as you're able to import the geometry and you're able to do it. You can model any size in Flux. So your three-phase, single-phase auto transformers, reactors, any sort of transformation action, because it is basically an electromagnetic conversion. You can simulate them in Flux. You can do the no load, short circuit, inrush current, insulation test, thermal test, and strength test. I'll get into these tests and I'll showcase some results in the coming slides. Dedicated advanced methods. So just like how Flux is not meant for one particular application, we have a lot of post-processing context, which we call, after solving the model, you might want to visualize different quantities. So we have a lot of post-processing, what do you say, support that would give you different quantities that you would wish to visualize. Coming to sensors, so sensors is another very important, component, simply because they're very sensitive and very fragile in nature. So it's important that you are safeguarding your sensor at all times. So, for example, position and speed sensors have to be kept at an optimal distance, because they should not impede with the movement. They should not be affected by the movement of whatever is moving, but at the same time they should not be too far away as in to not receive response. So current sensors, which I will get into in detail, magnetoinductive foil sensor, and even non-destructive testing. You can visualize the eddy currents, the motion, and you can even pump currents and see the reaction of these sensors, if they are within the permissible limits or not. And yeah, of course, the results are what matters the most. This is an actuator which is run by Schneider. Schneider uses our solvers to visualize different quantities. So what all sorts of actuators we know, the circuit breakers, the protection relays, electromagnetic valves, and to a great extent even the loudspeakers can be simulated for low frequency applications in Flux. Closing and opening time can be visualized, which is very important because you want to know the fault time and how long it would take for your system to react to cover that fault, so that you will have the insulation design. This is a very important concept as far as power grid is concerned, that can be visualized and understood in Flux. And acceleration and speed, the speed of the distinct, that the harness qualities, the different electromagnetic quantities, and the effects of the induced current. What sort of current density you are seeing throughout the region? Will there be an insulation burnout? These are all things that you can predict just by looking at these quantities, and also you can do it with co-simulation. Insulation in medium voltage and high voltage equipment. So this is a very important concept, because usually if these insulations is tested out in a laboratory, it's destructive in nature, in the sense that you are going to be spending a lot of time and money on understanding what this uh, you know solution is going to work, how it's going to work out in the real world. So we can definitely change materials, see all sorts of different, so we have complete flexibility on how you want to design the system, or how you want to visualize the system. So we have something called the streamer criterion, which is simulated in the post-processing context, where you can see the introduction voltage at which there will be a streamer between the ground electrode and the high voltage electrode. So you can visualize these streamers at what voltage, the inception voltage is the technical term. At what voltage would a streamer be formed between the ground and the high voltage electrode? All these are very important quantities that you have to consider while designing uh, a, this component for any sort of system, be it a microgrid or the entire country's grid. These are very important quantities. So you can see the effects of nonlinear materials, which is being used more and more today in insulators, and even the dielectric losses that you would incur by using these materials, and the potential maps and the electric fields and all of those things. So Simulating insulation might seem very silly, but at the same time, it's very important, because the results that you get speak a lot about what sort of faults your system can handle, and what sort of errors your system can handle, and what sort of adverse conditions that your system can go through without causing complete breakdown. So grid outage is something that we try to avoid as much as possible in today's environment, in today's world, because it's very important. We know how in the developed countries, if the power goes even for an hour, we are losing millions and billions of dollars. So it's a big deal, and in simulating these simulation insulation equipment is equally important. Speaking of induction heating, it's although it's not our main focus for today, it's important to know that induction heating can also be simulated in flux. So, in case any of your materials or any of your power grid equipment is going through some sort of it's going through some sort of heating, definitely you would face some metallurgical changes in the chemical composition of the material that is being used. So you can also visualize the same. All the different quantities that are associated with it can also be visualized. Power cables, like I said before, it's very important to simulate cables as well, because sometimes the buried cables or undersea cables are laid and forgotten. So it's like the fit and forget concept. You will not look back on them. You will not. You would prefer not to replace them if given an opportunity. So the important values, the effect of the inductance and the capacitances in this thing, what would be the power factor of the cable at the end, so the receiving end and the transmitting end, what would be the power factor, what would be the effect on the power that is being transmitted, is there a voltage drop or a voltage increase, is there an induced phase. All these things can be visualized in flux. You can even visualize the skin and proximity effects. So for high voltage high voltage 50 hertz voltages, you will see that there will be a good amount of skin and proximity effect, in the sense that the skin of the conductor will experience a lot of losses and will definitely have an increase in temperature. You can visualize this, the joule losses or the I square R losses, the rise in temperature, the electrical stress. So there will be forces between these cables that could damage the insulation, or any layer that you have can be damaged, which could throw for a toss the entire integrity of the cable. So all this can be simulated. And power connections. So definitely at the end goal, when and at substations and so on, we definitely have a lot of bus bars and a lot of connecting equipment, which have to be simulated, simply because you want to know what sort of bus bars or what configuration of bus bars will have least influence on each other. This I will get into the configuration. I will get into in the coming slides. So power modules also can be simulated in flux, like I said before. So in case you have an extensive numerical what do you say relay, and they have some sort of high current input or something of that sort, you can definitely simulate them as well. Jumping into flux, so flux, like I said, is a finite element tool, and we have three applications per se. You can simulate magnetic quantities, electric quantities, or thermal quantities. We have different types of analysis. So static, with the magnetostatic to be precise. If you have a time invariant field, for example, you can simulate in magnetostatic. AC steady state is definitely the frequency domain. So if you have harmonic components of your frequency, you can simulate them in AC steady state. And then comes the transient, which is the time variant. So you can all the lightning conditions and all the time, basically everything that changes with respect to time can be simulated in transient. So starting of generators, lightning, or fault conditions, all this fall in transient. So flux also allows couplings, like I said before. You can couple it with an electric circuit, or you can even give a motion, a linear motion or a rotational motion, depending on your application. We also have co-simulation. So magnetothermal and electrothermal can be simulated in flux. Why these are important, why magnetothermal and electrothermal create a big difference for a designer or a simulator, I will get into in the coming slides. And we also allow coupling with other third-party softwares as well, like MATLAB and all. So, like I said before, Flux uses finite element tool, but Flux Peak is another dimension within Flux, which allows partial element equivalent circuit method. So here you would compute a different set of values, which I would get into in the coming slides. But Before it was known as Inca 3D and was very widely used. Now it's all available within one software itself called Flux. So what is the finite element method? So finite element method is basically if you have an entire domain and you're simulating the entire component for say the flux density, it doesn't make sense to compute it as an entire body in itself, because at different points you have different sorts of what do you say, different values of these quantities, and different vectors in different directions can be seen. So what finite element method basically refers to is the division of this entire geometry into smaller parts, basically tetrahedrons, hexahedrons, prisms, and pyramids, so that we can find the quantity of whatever which are electromagnetic quantity, whichever we are trying to focus on in this particular cut down element, and then the entire domain can be visualized and then integrated to get the entire domain's reaction or response. Flux peak, like I said before, is a partial element equivalent circuit method. You are directly giving the circuit and coupling it with the geometry here. There is, you want to visualize the parasitic impedances and capacitances in the entire domain. So what we do is the fast multipole method, and by integrating the entire air. So there is no requirement of air meshing, and skin and proximity effects are taken into account by default. So this is another exclusively for bus bars and single level PCBs and all of that. We offer Flux 2D, Flux Q, and Flux 3D for finite element solving, and Flux Peak is another dimension in itself. So when I say Flux 2D, we basically refer to a 2D plane which is along the y-axis. So for example, a motor. So if you see here in this image, you can see that we have a motor that is in a 2D plane, and along the y-axis it is taken as symmetric. And or you can do axisymmetric. Axisymmetric basically refers to what do you say, the symmetry along the axis. So symmetry along the axis. So this is a rotary element. So you can take it as a circular or a cylindrical element. It's a little difficult to visualize, but once you get into simulating these, it becomes a very common nomenclature and makes a lot more sense to you. The reason why 2D is used extensively is because it's very easy to use. You do not need to spend a lot of time setting up the project or setting up your definition, and it's very fast when compared to 3D in the sense that it takes much lesser time to solve. So say your 3D project for back EMF of a generator takes somewhere around maybe depending on the size of a generator, anywhere between 6 hours to 3 days. But in 2D, it would take like anywhere between 2 minutes to maximum of 6 hours if you're solving it for multiple steps. So a lot of factors are to be considered when you are considering the computation time, but definitely 3D will take a lot more time than 2D, and you get a good approximation in many cases. So in today's world, not a lot of what do you say, components are the same along a single axis, because we have lots of advancements and lots of design changes and lots of patents that are being thrown into design components. You get a good approximation in many cases, but 3D will definitely be more accurate. So yeah, the disadvantage being 3D effects, like say for example, the end ring of an induction motor cannot be considered here, or for example, the end winding of a generator and the effect of the end winding cannot be considered here, or the magnetic circuit effects of an actuator or a sensor cannot be considered here. And some devices, very rarely, some devices cannot be modeled in 2D. Flux Q is strictly for electrical rotating machines. So we have seen skewing of rotor or stator for cutting down the torque ripple or the cogging torque for better performance of the machine. All those we have seen skewing. And the advantage of this is we call it 2.5D, in the sense that we set up the project in 2D, but it solves to 3D. So it's very beneficial when you are looking for quick results. And a lot of our clients who have skewed motors definitely use this for simulating. The only disadvantage being, again, we are not considering the end windings or the end ring, simply because you're setting it up in 2D. Flux 3D is what is extensively used by the global manufacturers, because they require very accurate results as they are developing the characteristics of their components. They require very, very accurate results, so they prefer simulating the entire model in 3D. So 3D is, like I said before, very accurate in the sense that it gives you the most accurate results, because all parameters are taken into consideration. The disadvantages are definitely it takes a lot of set time to set up. So meshing, which is a very important process in finite element solvers, you will see it takes a lot of time, and the solving time also is very large. The results that you can expect are electric, magnetic, thermal, and partial element equivalent results. Coming to the electric application, you can visualize the dielectric breakdown, the dielectric losses, electric conduction, the current density, the magnetic field due to corrosion current. So this is again a ship magnetic structure signature, and even the transient electric field like lightning tests and all of this can be done. In magnetic, you can see a lot about the inductances, the DC losses, the induced current effects, the inrush current for transformers, which speak about the aging of the transformer. All that can be visualized, and even the harmonic content of the what do you say, the losses and what sort of the different inputs. So since we have complete control over the electric circuit, we can give different sort of inputs, maybe sinusoidal, maybe DC, maybe square wave, and see the reaction of all these components. Definitely, even the losses in different regions, in the magnets, in the laminated region, in the solid region, all this can be visualized. And any shape, there is no shape restriction in flux. You can simulate it to any shape, whichever shape befits your application. You can simulate it in any shape. Then comes the thermal application. So Flux is not a thermal tool because we do not use computational fluid dynamics or CFD per se in Flux. We use finite elements. So, for example, if you're simulating a component, you can definitely see thermal signature of the component. But to take into account the real world, flow of air and flow of coolant and all these things, we have AccuSolve. So, Flux, you will export the losses from Flux to AccuSolve, and then you will visualize these results. So you can definitely give the convection coefficients at different regions and all of that. But then again, we call it the first level of thermal simulation. So if you're in the initial stages of your design, or if you're initial stages of simulation, if you want to know what sort of temperatures your machine might reach, and if your design is appropriate, you can definitely go into the thermal application. So the flux peak, the impedance is the biggest characteristic of a bus bar, simply because it can bring in a lot of difference in the what do you say in the uh, performance of the impedance in general. So the power losses, the inductance, the parasitic capacitance, the forces that are acting on the bus bars, the radiated field and the influence of frequency at different domains, the phase changes that they bring in, all these make a big effect on your entire bus bar system. And even though it seems fairly simple, like you could just randomly place three bus bars and send current, or send power across it, the position of bus bars with respect to their faces, as we all know, make a big difference. If they are not spaced correctly apart, the mutual inductance, just like how power lines interact with each other, even bus bars interact with each other. So it's very important to understand what would be the input impedance, the output impedance, which dictate the power flow, is very important while simulating these while designing these components. Flux as a tool allows a fair bit of geometry changes. So if you are importing, say for example, an actuator or a sensor, you want to make some small changes, you can definitely do it. But Flux, like we always say in Altair, is not a CAD tool, in the sense that we do not have the same extravagant options that CAD tools like AutoCAD or SimSolid or Parasolid offer for geometrical changes. But we do support import of all sorts of CAD formats, AutoCAD, STEP, IGS, any format you can import, and you can simulate the same in finite element solving. But most of the times what happens is that your electromagnetic component will have a lot of mechanical supporters. For example, a spring or a plastic casing, or all these mechanical supporters, which do not actually speak about the electromagnetic performance of the component. So yeah, those kind of changes where you want to remove these components or remove these volumes that have no effect on your electromagnetic performance, you can do it in Flux. So meshing is, like I said before, a very important part of finite element solving. And it is very important for your results. So if you want to get very accurate results, you definitely require a fine mesh. So when I said before, the entire geometry is cut into small prisms and tetrahedrons and quadrahedrons and whatnot, it is very important that you have it very fine in regions where maximum energy conversion is occurring. So for example, the air gap of a stator and a rotor is where maximum energy conversion happens. So your electromagnetic energy is being converted into mechanical energy, which is like, very high amount of flow, and a very high amount of changes occur in a very small region. So it is very important to mesh these regions very finely, and the rest of the regions where, the stator core or the rotor core or the transformers core, very few amount of changes occur, and a generalized changes can be visualized. So it's very important your mesh is appropriate to your project. Why I say it's appropriate to your project is, if you have too fine a mesh throughout the project, that will increase your solving time. So it depends on how many nodes, and it also increase your computation power that you require. You might one CPU with 12 cores might not be sufficient to simulate such a project, or even if it is sufficient, it might take a lot of time to go through the linear solving process and the non-linear solving process and all of that. So there's a good trade-off that you have to do with meshing. So Flux offers the user complete control over the mesh. You can define how you want to mesh the entire domain. Or if you are not a mesh expert and you are new to meshing, we also have something called an aided mesh or an automatic mesh. So the algorithm basically finds regions which have, like, a possibility of interaction. So if there is a a small gap between two objects, the algorithm identifies that gap and finite, like, gives very fine elements in that region. So this can also be done. We also have an automatic option, we also have like customized option, and we also have a neutral option where you can set the coefficients of automatic mesh as well. So all sorts of meshing is possible in Flux. In case Flux doesn't give you enough options to mesh, we also have other meshing tools, which are Hypermesh, which is like one of the best tools in the market today to mesh domains. You can import the mesh from there as well. So a wide range of options. Like I said before, it's very important to have clean geometries while doing finite element solving. If you have geometries that have very small distance between them, it can throw an error or throw the entire solving into an infinite loop. So it's very important to have a clean finite element based geometry for solving the same, and Flux allows you to, like, simplify and all of that. Then comes the physical properties. So it's as important as geometry and meshing is, if your physical properties are not correct, in the sense that you're not assigning the correct materials or not pumping the right amount of current, your results will definitely vary from the real world results. So Flux offers a lot of options for all these quantities that you can visualize. So non-meshed coil is a concept that is used in Flux for coils that around an actuator or in a motor. So meshing, like I said before, speaks about the solving time. So to avoid that amount, that much solving time, we have something called a non-meshed coil. So we use the Biot-Savart's law to compute the effect of these non-meshed coils on the meshed domain. So it's a beautiful coupling between the two, and it's actually very nice to see how the time taken is reduced to significantly. Then yes, we have surface models, in the sense that you can assign regions. So if you have, like, for example, an actuator which is being placed very next to a coolant. So on one part of the actuator you have a coolant flowing, so you can definitely assign that face region as with a different convection coefficient or a different radiation coefficient per se, and simulate the system for thermal. So we have allow all sorts of region, line regions, phase regions, volume regions to be defined. Hysteresis modeling. So I'll get into that in power transformers. So we all know the aging effect of transformers with inrush current hysteresis modeling. That can be done in the post processing and pre processing actually of flux. Skin and proximity losses in winding. So this is a concept that is very difficult to simulate, in the sense that it's very difficult to geometrically define what do you say, a transformer in its entirety. As we all know, a transformer is a fairly complex device. The windings and the core and the lamination, the air gap, it's a fairly complex device. It's very rarely do we ever get to see a perfectly drawn realistic transformer that can be simulated as same. And even if we do visualize individual conductors, it's very difficult to mesh each one of those conductors and see the effect on each one of conductors, and it will take a lot of time. So most of the times what designers do is assign one entire region as coil conductor. They won't give individual what do you say, individual wires or such. We'll give an entire region as a coil conductor. So it's important to visualize them, and we have a lot of macros. Flux allows a lot of macros and a lot of tools that will help you simulate the same. Skewing effect, which I'll not get into because we are not looking at skewing today, and demagnetization of permanent magnets. So if you have a magnetic gear and you want to see how, if they're ever going to be demagnetized at a certain RPM or at a certain temperature, you can definitely visualize them as well. Flux works mainly on Python. So the entire tool is based on Python. So we have a live Python scripter and recorder available, and most tools these days have a live Python bit, because it's the most widely used tool for machine learning, and because we are doing something with design, it's very easy to correlate these with machine learning and get optimum results. So as you can see here in this image or in this GIF, you can see that this width of the stator tooth is being simulated for different sizes, and the effect on the torque is again visualized. So this might seem like a very long problem, in the sense that it took a lot of time to solve it. This is a SPM motor, a surface permanent magnet motor. It might seem like it took a lot of time to solve it, but because of parametric solving and distributed parametric solving, we are able to create individual jobs of various thicknesses each and place it on each core, and then simultaneously run these. So you can see, we've reduced the time taken with the increment of cores. With the more number of cores, you can reduce the parametric studies time taken. So this is, again, we have a lot of nonlinear solvers. We have a lot of different methods: the global optimization method, the Fujiwara method, Newton-Raphson solvers of different Newton-Raphson solvers of different sorts. All these are available for your own, advanced flexibility on how the project solves. So everything from basic mathematical equations to scripting and computer programming knowledge is being used in designing electrical systems. Post-processing context. So this is one of the most important, contexts in any software, be it AccuSolver, be it, Flux or Flux Motor, any of those softwares. It's very important that we get the results we wish to visualize. So like I said before, since we do not have one single application, a wide variety of, values can be visualized and can be plotted, graphs, the 3D graphs, 2D graphs, potential lines, even flux density, losses in the entire region. All these can be definitely visualized and even exported to, different contexts. So you can export it as a text file or an Excel file or whatever format you want it to, and then visualize them in your context. So we have a wide variety of, quantities that can be visualized in different patterns and different ways. This is something to speak about the accuracy of software. So when you speak about any sort of simulation software, it's very important that they are very accurate, in the sense that they're as close to real world as possible. Because when you're in the design phase of some tool, and if your design and your prototype do not correlate with each other, it definitely throws into question about your entire design knowledge. So it's very important that your simulation and your uh, you know um, your actual results are very distinct. So most of the time we see very good accuracy. Like I can see here, we have a less than 1% error between the simulation and the actual result. So the dotted line refers to the simulation, and the blue and pink lines, or the blue and purple lines per se, refer to the different, what do you say, measurements, the different mesh measurements in the simulation, I mean in the real world, this thing. So we have less than 1% difference here, but most of the time, 99% of the time, we have a plus or minus 2% variation, and that's it. So your accuracy is really good if you've done your project appropriately. So accuracy again depends on how you define your physical features. If you've got your material data, the BH curve of your material data, the electrical resistivity of your material data, all these are very important quantities that you will need to give as inputs to Flux. This is another very important concept. So iron losses is one of the biggest form of electromagnetic losses, and one of the most constant form of electromagnetic losses. And even though in, what do you say, in laminated regions we say it's very less, it's one that speaks about, the constant sort of losses that you can expect. So it's very important we have a really good understanding of these losses, a really good understanding of how these losses are being taken into consideration, and how you can, make them better, because they also contribute to total general heat dissipation in the entire geometry. So yes, we have different ion loss prediction models like Bertotti's and Ellis loss surface method that you can compute for different sorts of materials. Like I said before, Python. So Pythons are base language. If you are a good scripter and if you want to automate something that you're repetitively doing, you can do it with Python. So Python is equally important in designing electrical equipment today. And since a lot of our users keep giving us requests for something that they're repetitively doing. So if I say, for example, they want to find the region with the maximum what do you say flux density, this thing. So we have a macro, we develop a macro for them and we put it in our list of macros that you can import into your project and do the repetitive process again and again. And then we have APIs. You can couple with APIs. You can, if you want to use VBS or Java, you can use an API, and you can even use Excel to run Flux. So it's how you want to use the tool. It's how you want to visualize and use the tool. So yeah, definitely a lot of this customization and optimization, automation of this software is definitely possible. Again, for like Simulink, Altair has our own 1D simulator called Activate, where we can simulate real world scenarios with feedback of a component, and all of those visualized. These things can be visualized. In case you have a hardware in loop system like Opal or something like that, you can export the component that you have as in the form of a lookup table or an FMU block into your hardware in loop system and then simulate. So say, for example, just to give you an idea of what I mean when I say hardware in loop is, say for example, you're simulating a power controller and you want to see the motor response, but you have the power controller and you don't have a motor. So what you do is you connect this power controller to a hardware in loop system and take the motor as a lookup table. So you can see the output across your motor from your power converter just by as an entire system. So it's a very exciting concept, and yes, Flux does definitely allows you for this. Optimization is something that people consider as the last step in simulation, because you want to optimize your design. So most of the times what happens is that we have the manufacturing capabilities to change the design, but we do not know in which direction we should change the design to achieve the result, to achieve a better result, because what design we have started off with might seem optimal, but definitely there's always room for growth. So maybe skewing, which skew angle would be appropriate for your application, or the magnet dimensions, the magnet size for a PMSM motor, a BLDC motor, for a generator, the coil winding factors. All these things are very important, to the number of turns. All these things are very important, and there will be an optimal value at which you will have maximum efficiency or maximum output from your component. So you can definitely, put in a lot of different models into HyperStudy, which is another tool again within Altair. It's an iterative study. You can use different methods, such as the global optimization method, so different mathematical formulas that are used to find the best, iteration or the best design possible given the upper and lower limit constraints. Speaking about that in the coming slides. So now I will jump into the power grid equipment domain. So now that I have spoken about the software and the tool and how these tools work and what are the different this thing, now we can see how to use these tools, for different sort of applications, and what would make the most amount of sense for each of them. So yeah, the global trends, we have, something that is with developing economies. So like India, and with the inflow of manufacturing technology into India, we are seeing a growth in construction, and very urgent requirement in developing not only talent but also the resources to be, it has to be transported to the right location. So which includes power as well. So the entire nation's economy is dependent on the power grid and how much power we are able to give as an output. So it's very important that developing economies, especially like India, have an ever-growing grid, when basically a sustainable ever-growing grid that increases the output but decreases the negative effects on the entire country and the planet in general. Then again, we have utilities. So during the lockdown, we have seen a very great increment in power taken into homes. So usually industrial areas are supplied with more power during the day, but now with everybody staying at home and everybody preferring to work from home and all of that, a lot of power is very distributed. It's no longer concentrated in one region, so you do not have to focus, on that one particular region, but on the entire grid in itself. So utilities are increasing. We are using lots of power for everyday household activities. And before, we did not even have the concept of Wi-Fi, but now Wi-Fi is on every 24/7 in everybody's houses. So again, utilities are increasing. And then smart grid technology, we are trying to automate everything. Like basically whatever we can automate, we want to automate, because human error is something that we do not want to go through or face, because grid outages and all of those things are causing lots of losses. So smart grid technology and automation is requesting more energy be drawn into the domain. So all in all, the grid itself is actually demanding more from design engineers and designers per se. So it's very important that we match up to this power grid requirement. So, like I said, there are multiple components in the entire power grid. So, from generation, depending on which source you are generating, it's very important we design efficient generating equipment. And one way to do that is with simulation and optimization. Transportation of this energy is very important, because we have something called HVDC transportation these days, which, or MVDC, which even Bangalore has, an 800 kilovolt line, DC line, being laid right through the city. So it's something that people are definitely looking towards. That a lot of new experimental technologies are being implemented worldwide to see, their effect on the entire grid, their performance characteristics, and so on and so forth. Distribution is very important, simply because isolated incidents in particular requirements. So say industry X, industry Y, and industry Z are on the same grid, and industry X went through some fault and the entire thing shut off. It shouldn't have a global impact on the entire grid, but instead only industry X should have some sort of individual safety requirements. So coming to that, it increases the requirement for all these safety devices and all these isolators, relays, and all of that. Then comes the services. So you want to definitely be very open or transparent as a utilities company to your clients and to your this thing, because um, power is a very important resource that a lot of industries consider, a very important natural resource that speaks about their pricing and their, a lot of industries look at power as, and as a raw material. They treat it like a raw material simply because it has a very great impact on their output and their production. So yes, this all put together definitely throws a challenge for power grid designers. As you can see, the worldwide energy requirement is increasing, and even the generation is increasing. So in developed countries like the European countries, or in North America, where we have America and Canada, there isn't a huge amount of increase. Like, it's very minimal. But in developing countries, like in the continent of Asia, with India, China, Thailand, and all these countries which are manufacturing a lot of these things, which are becoming the manufacturing hubs of the world per se, require a lot of, like, you can see the generation has increased, like almost 5 to 10 fold, with a lot of focus being on reliable and what do you say, um, green sources, so that we do not have a lot of like great impact on the environment as well. Going on, moving forward, the market in Africa, Middle East, and Latin America do have a great increment, I mean, great requirement of energy, but Asia definitely, with respect to India at least, has a very great increment. I mean, request for energy generation. When it comes to countries, developed countries like Europe and North America, they are looking for increasing the efficiency of existing grids. So currently their efficiency is somewhere around 70%. They want to increase those efficiencies. So that means that they are looking at redesigning of components of every sector, right? From simple relays and bus bars to power transformers, distribution transformers, entire grids. They're looking for better efficiency and all these things. So there is a global demand, not only for the engineers who design these equipment, but also for tools that help them improve their efficiency and reduce the cost, and reduce the effect on the environment at the same time. So when you consider distribution, cost is the important factor. You know, money is king in all in all scenarios. So as you can see, cost demands, you know, losses and temperature reduction, mechanical weight reduction, and insulation has to be appropriate. You do not want to have too much insulation or too little insulation. All these things are very important factors that have to be considered. Simultaneously, we also have tools which can visualize and, you know, give you appropriate results of the same. So for insulation design, the thermal characteristics of the insulator is the most important part. So for insulation design, we have thermal analysis solvers like AccuSolve, which work on computational fluid dynamics. For losses, which I like I said before, flux gives you the losses and temperature distribution in the entire region. And for mechanical understanding or weight reduction or, you know, impact reduction, we have something called as Altair OptiStruct for the same. Let's just dive into you know, some of the applications like I said before. This is something regarding the cable characteristics. So capacitance matrix and all these things are very important. So you can model in 2D, you know, you can model in 2D for how much ever length you want, because the axial length is an input. You can give whatever length you want. But the effects of 3D cannot be taken into consideration, in the sense that the axial effects of the cable cannot be taken into consideration. You can definitely simulate the same in 3D as well, with giving like an infinite conductor. You want to compute the inductance per meter, the resistance per meter in steady state as AC application, because they are the characteristics of your cable. You know, they refer to basically the data sheet of your cable. Even before putting into service, as a designer, that is the data sheet of your cable. And then the compute capacitance matrix in the you know, static electrostatic application. So the electric capacitance matrix can also be simulated. Coming to the inductance computation, we can use you know, different depending on what sort of inductance you want to see, mutual inductance or self inductance. You can you pump current through one cable or two cables or all three cables, depending on how many phases you have in the cable. And you can use the formula and you can figure out the electromagnetic energy, and with the energy we can compute the what do you say, inductance as well. So here you can see in this equation, L equivalent is what you want to compute. So you get the energy, you know, the number of the cable, and you know the current that is being pumped. So the equation will change with LEQ coming on the LHS and E coming on the RHS, and then you can solve for the equivalent inductance. The resistance also speaks about the power loss in you know, the resistance actually defines the power loss in the cable. The global losses in the cable is given by the resistance. So we use the, you know, the I square R formula, the most understood formula in electrical engineering, where we say P is equal to I square R, which is the losses in the region. In any electrical region, the thermal losses or the joule losses is directly equated to I square R. That can also be simulated and understood in flux. Capacitance matrix computation, like we all know, is a little complicated depending on how many phases you have and how many screens you have, and you know, the total you know, cable length and all of that. So we have we propose two methods. One is the energy method and the other one is the float potential method. Speaking of the energy method, we have n square computation. So if you have n number of cables, you will have to compute n square times. And then, you know, the voltage, like you can see the formulas here, the capacitance is given by the voltage that is being pumped. And we've all done this in power system analysis. It's a very common thing. And then you compute the Kirchhoff matrix, through which you compute the capacitance matrix. The other one is the float potential method. The float potential method definitely requires only n number of computations, but the problem arises when you have to compute the inverse of a matrix. So flux as a tool, we do not yet have the inverse of a matrix computation. Like, you cannot do it in the software. You'll have to take it out and then, you know, maybe run it through Java or any other you know, automating method to compute the inverse of the matrix. But since this has the inverse of the matrix in this thing, float potential method has the inverse of the matrix, we do not use this method in flux. We use the energy method. Although it takes n square computations, it's much simpler for your computer, like for your computer to handle. At the end of the day, it's how much computation power you have, you know, what sort of cores, I mean, what sort of RAM and memory, what sort of system you have. So we have seen that the energy method gives accurate results and you know, does not take a huge load on your computers at the same time. This is something, again, lossless computation in the bus bar system is very important, simply because, like I said before, the bus bar can throw a wrench into your perfectly oiled machine if it doesn't function appropriately. So although there is no magnetic material in the region, it's just an electric this thing at the joints where you are putting your what do you say, your conductor, where you're connecting your conductor to the bus bar. You want to see the dissipation of energy from one point to the other. You can definitely visualize those losses, in which region what sort of losses are occurring. And if you have too many joints also, there can be a region, I mean, loss area. If you have what do you say, bends, and what are the effect of these bends and the position, and all this can be visualized in flux peak. um, Coming to, yeah, so with with increase in frequency, so we definitely know that frequency remains constant, but there will be some harmonics in your input. You can definitely visualize the effect of these harmonics in your bus bar system and your entire domain. This is one example. Schneider used, to design their medium and low voltage equipment with power switches, relays, and current sensors, and even their power transformers to simulate the same. So as you can see here in this image on the lower right-hand side, the entire casing is plastic, and there are a lot of non-electromagnetic components. So while simulating, only the inside magnetic component and the magnetic circuit is simulated. Although it's an entire box, the actuating part is only such a small part. So it's important we understand that we can only simulate and only need to simulate this part itself. There is another tripping unit, and that they used for simulating and understanding the performance of this tripping unit. So it was basically solenoid. The tripping unit was a solenoid with a moving part, a bobbin pin, which was controlled by an electronic circuit which monitored some parameters on the grid, or whichever line it was connected to. So they used parametric computations to find the optimal size of this thing, the optimal number of turns, and then used system level tools. And then they got very important parameters such as the temperature, the coil resistance, the impact of the voltage in case of harmonics, or if there's any fluctuations in the input voltage, what would be the reaction. The corner case validation. The corner case validation means in a scenario where the device is cornered into protecting the system but at personal loss. So basically the device has to protect the grid even if if it's destructive in nature. So that can also be simulated and understood. And even the sensitivity of the entire this thing, at what point the tripping condition occurs, all this can be done, and we had very good agreement with the measurements. These are some ideas of the gas insulated switch gears. So with onset of new technology, we have seen a lot of things, a lot of varied parts of the component being changed. Everything from the number of turns, which have been conventionally being optimized since time immemorial, to materials today which are very important, like for example SF6 gas, which is something that people are using extensively in small. We have seen how the SF6 gas reduces the size of the entire substation or power station. So the simulating these also is very important. So flux allows, not only flux, actually a lot of tools allow this sort of flexibility to simulate different new modern technology that you want to experiment with, see the results with, even before investing any money into procuring these elements and procuring these materials to simulate them in real time. So now let's just jump into power transformer. So like I said, we are expecting to increase efficiencies, and on 2021, guarantee of load loss around 30% less than 2016. So as you can see, in a gap of 5 years, our load losses have to be have reduced by around 30%. And all this is thanks to simulation of these machines and understanding where these maximum losses occur. What is it in the design that is throwing these components with such huge losses? And then we have new methods of computation of efficiency. So we no longer follow the conventional efficiency computation for motors. So we had something very commonly which we learn as all-day efficiency, and different quantities of efficiency that we consider. We no longer consider those. The all-day efficiency now is a rather outdated concept in developed countries, at least, where they have a new method called the PEI method. If you are interested, you'll have to read about it. It's a fairly complex method of computation, but it is more realistic in nature. The specific requirements. So different types of energy sources with increase in sustainable sources that are being exploited for energy, with different varieties of sources. It's very important to develop special kinds of transformers. So we might have a low voltage input that has to be connected to the grid. So from a very low voltage, stepping it up to a very high voltage is, a rather tremendous task for a transformer. So that also needs to be considered. And if you have multiple, regions of connection, if it's a three-phase connector, all those things, though, all of them need to be simulated appropriately. And then yes, overcurrent harmonics to understand the aging effect on the motor. All this can be simulated. Then the quality of the material and the motor, that is, quality of the transformer that is being simulated, in which speaks about the life cycle, the aging effect. All this can be simulated, and you can even give real world test scenarios which can directly give you fault conditions. So at the end of every user manual we see these fault conditions and appropriate reactions. So most of the times people cannot test these huge for power transformers for such fault conditions. That's why we simulate those conditions and give appropriate results. So you want to visualize, the precise losses, the localization, where it is having the what sort of losses, and you want to optimize their efficiency. You want to decrease the insulation distance. So basically, you don't want to have a lot of insulation, because then it can have an inductance. It can have an effect on the stray capacitance and inductances. You want to decrease the raw material cost, because cost drives the grid, as we say today. And you also want to use different tests on the entire geometry to speak about the characteristics of the machine, and if possible even optimize these things. So with transformers, although from an electrical point of view we see the short circuit and the no load test and all of these things, there's something called the thermal test and the strength test on the transformer, which is very important. So in flux, we can do it in 2D or 3D. As you can see here on the left-hand side, we have it in 2D. The red, the green, and the blue, light blue, speak about the the coils which are wound around these three arms of the transformer, with a laminated air gap region in between. So this is like a very realistic design of a transformer, so that we do not have a complete magnetic circuit. So shorting them would be like inviting trouble. So we do not usually short them completely. There is a air gap of some sorts between these regions, or laminated regions. You can do that in flux. You can either import the geometry, or you can develop the geometry in flux itself, and you can parameterize for design exploration. We have different levels of macros available, which I will get into the next slide. You can see the exact point, exact plane of what sort of effect is being taken into consideration, even the air gap. So as you can see here, the coil is being simulated as perfectly aligned. So rarely do we align coils this perfectly, but we have a general idea of how much distance is there between each coil. So we can definitely simulate them with perfect this thing, and see, or have at least some sort of basic understanding of what sort of winding is required, what would be the optimal distance to have very less skin and proximity effect, and all these things. And even the homogenized materials, all these things which speak about the characteristics of the transformer. So representing the transformer, like it's a common query. So if you have a transformer of this sort, how are you speaking about the the current that you're pushing in, or the no load test or the full load test? Because in real world we always have an auto transformer that we are connected to a transformer, and then we're rotating it, and we're seeing the primary and the secondary side. This thing, how do we do it in flux? Well, in flux, we, like I said before, we can define the electrical circuit, and in the circuit you can give different. So if you have a voltage source, you can give a voltage source. If you have a current source, you can give a current source, and you can pump current into the primary and then see the reaction in the secondary. So all this is you can do it real time, and it's very important to model them appropriately, simply because the results depend on your input. So as you can see here, there is R1, R2, R3, which speak about the secondary resistance. So this is a component that you will have to compute from the resistivity of the material as you give an input. Flux will not automatically compute this, but you can definitely give, if you're in the design phase, in the preliminary stages of your design, you can give some random value, and then just check the reaction, what sort of resistivity you expect to have based on your previous designs. All this can be visualized. Um, Laminated magnetic cores is something that is very complex and something that throws your entire model for a toss, because the eddy current losses in that region has changed. The configuration has changed. So, in which direction should you laminate the cores? If it should it be at planar with the XZ axis or with the XY axis? Because even then, your face has to be taken into consideration. So this again, which direction should it be laminated in is a big question. So as you can see here in the lower region, you can see that we have parametrically solved for the angle here and 0 10 degree, which angle the lamination is occurring at, and you can see the effect of what angle and what sort of BH curve we are achieving from them. So this is the material BH curves. So according to your material BH curves, you can predict your eddy current losses, what sort of phase difference it will give in your material, and all of those things can be visualized. And this is all in the design phase. You still haven't put any money into procuring materials or even started designing this thing. So this will definitely help you in understanding the effect of these laminated cores. So yes, like I said before, we have something called as non-meshed coils, which allows for transformers for quick design, and it doesn't take much time. Different parameters are there that you can define. Um, if you do go ahead with, it's a trade-off. It's at the end of the day, it's a very generic trade-off, where you are deciding if you want supremely accurate results after 5 days, or if you want very good results after 1 day, I mean after 1 hour. So it's a big trade-off that you have to make. So usually in the final stages of your design, where you are trying to fix the design, that is where people usually go for very accurate modeling of your component. In case you're in the preliminary stages, like I said before, you want quick results, you want to quickly do it. So the general human trend is it has nothing to do with the software or anything, but general human trend is that you have the tool reacting and giving you results as and when you go. So Flux allows for all those types of studies that you want to change. This is an example of a no-load test simulation. So since Flux is a finite element tool, you will have to physically you will have to manually calculate some of the quantities that you wish to visualize. So if you want to see the impact of the test or the current that you're pushing through the primary, or the voltage that you're pushing through the primary, you will have to manually calculate the impact of it on the secondary and then visualize. So you can see here in the red box, we have something it represents a transformer in the conventional sense, and everything outside it is just to visualize the results of sorts. And if you want to see the phase difference, we'll obviously plot the current and the voltage on R1 and the voltage from V1 and see the difference between them. So these are all manual calculations that you would do, and you would understand the magnetizing current, the reactive power per phase. So the reactive power is basically an angle which will give you, the phase difference, and the magnetic inductance in the core from the different materials that are being computed. The short circuit tests, yes, it's a fairly complicated test to set up. We have to test a short circuit case. So if you have more number of phases, as you can see here, we are pumping it through the primary, and there's a tap turn in present, and then there's a secondary and tertiary short circuit as well. So the magnetizing current is again neglected because you cannot visualize the same. So we have the magnetizing current from the previous test, so you can add that magnetizing current here, and you can visualize the flux leakage. So these formula give directly the energy loss and the power loss from the entire region, which will then give you the joule losses. So in short circuit tests, we mainly visualize the joule losses. So that's why we, even in the lab, when we are doing a short circuit test, we do not let it, go on for a long period of time. It might burn out the motor. But here you can, run it for how much ever time and see whatever sort of this thing you want to visualize, and then you can visualize the joule losses. So at what instant will breakdown occur in case there is a short circuit? At what instance will the breakdown occur, the thermal breakdown or the insulation breakdown? At what instance will it occur? You can predict all these things and then speak about the characteristic of your transformer, where we say the fault characteristic threshold, where you give the time of how long this component can withhold. This can be done in the short circuit test simulation. There are a few results in the mechanical structure, so you can see different components and the effect. So if there is a short circuit, which component is going to be having the most amount of forces and the most amount of losses, and all of that can be done. Inrush current simulation speaks about the resonance effect. So this is something that is very important, and you can consider the hysteresis effect. So as you can see in the graph here, this is the current without hysteresis. So current is pumped till here, and then the current source is switched off, and then after a certain amount of time, the current is pumped again. So the primary current, you can see, has bumped up to around almost 5 to 10 times of the original value. The secondary current has remained the same. So it's to understand the aging effect and the effect on the BH curve of your entire material. Interest current tests is done usually by manufacturers in to understand the life of the transformer. They usually say 25 years, 30 years. So they usually do an inrush current test to understand the material characteristics, how it is changing, and there are quite a few coefficients that you have to enter. This is a fairly complex test to simulate, but if you have all the quantities, so if the physics parameters, which we say, if you have all these quantities and value of alpha, A, X, C, and K, if you have all these quantities, you can definitely simulate them and speak about the aging of your transformer. Coming to insulation test, it's dielectric breakdown is something very common in power transformers and even in insulators. The electric field maps, the tank, the oil present in it, all these things have different breakdown inception. Sometimes even coils can spark with each other in case there's a insulation breakdown on the outer turpentine. I mean, what is that? On the outer insulation of the wire, then that can also cause a breakdown. So you can definitely visualize them as well. Like you can not only visualize, you can even compute, find the streamer criterion of that coil or the core or whatever, and even the effect of the oil around the tank, the losses in the oil, what sort of thermal distribution you can see. Will the oil age quicker? Will the oil burn out? Will the oil have some sort of negative effect? All this can be visualized in the insulation test. Speaking of the transient electrical application, the biggest faults in the world are all transient, in the sense that they do not last for a long amount of time, but they have a major impact on the grid. So it's important that we simulate and understand the characteristics and what is actually going on between each component, so that we can optimize that component. So if, say for example, the number of turns is in a transformer is what is the weak point of a transformer when there is a lightning this thing a lightning strike. You can definitely optimize that in the simulation phase itself. And you can use your own input, since it's completely a finite element tool and based on mathematical models. You can impose your own voltage of any value. You can visualize your, same whatever form you want to visualize it in, if it's a sinusoidal or exponential or trapezoidal or square or any sort of waveform that you want to visualize. You can definitely visualize that, and the biggest advantage being you are taking into account the non-linear materials. So non-linear materials, basically materials that change with respect to time, or their BH curve is a non-linear curve. Most of the time they are. But if all these things can be taken into consideration, even the temperature effect can be taken into consideration. These are the Laplace forces. So the forces on a transformer are very important because they speak about the integrity of the transformer's mechanical structure. So the coils experience some sort of forces. Say for example, like in the image shown here on the right, on the upper right corner, if you have a face within a face, and the forces are towards each other, or the forces are away from each other, the coupling factor and the air gap length and all of these things will definitely change. So there will be a change in your output. So what sort of harnessing is required to keep these coils in place? So these coils are not hovering in air, they are hardened or tied onto something so that they remain there. So what sort of harnessing is required? Where is the maximum amount of force that is being concentrated on? And the ability to take these into what do you say, third party mechanical solvers, so that you can even visualize the effect of mechanical components on these domains. Stress analysis. This is an example of stress analysis and obstacle. So as you can see here in the video, you can see in the GIF that the stress is pulling the coils together. So even though there are three different phases, they're experiencing some sort of force that is throwing the integrity of the transformer for a toss. So what sort of power can you, what sort of harnessing would you require? All this can be visualized. Where would breakage first occur? Where do you have to, even if you're going to visualize a transformer that has been in use for 20 years, you want to understand where to look for the, if it's a very big complex transformer, you want to know where to look. You will see the maximum stress points here. So as you can see in this GIF, the upper point here and the lower point here are in red. Basically means the maximum amount of force is experienced there. So it's throwing this entire thing for a toss. Then comes the thermal analysis. So different types of oils are being used for transformer oils, different configuration of oils. So just like alloys, manufacturers are experimenting with different combination of oils, which is optimum for cooling a transformer. Do we need a cooling circuit, or is stagnant oil enough? All these things can be simulated in AccuSolve, which is our CFD computation tool. And then definitely to understand the cooling systems and the effect of the oil on the tank and the surface area of the tank, if it is required to be increased or decreased, if we have room for all of that, that we'll get to in the optimization part. So we also have examples in Flux to visualize and to help you understand what and all can be done. So these examples have an in-depth document of what you are modeling, how you can model it. The tool has examples within itself. You do not require a tutorial to understand. I mean, you do not require a training to understand, because these documents are fairly in-depth. They speak about which option you have to select, and you can get started on with the tool as soon as you download the tool itself. Like I said before, we have some macros for computing different kinds of quantities. So based on our previous users and based on requests that we have got from clients and customers, we have developed macros for visualizing different quantities. So one of our customers was constantly visualizing the iron losses in the entire region in the form of this thing. So by default, Flux will not compute these losses during the solving process. So you can use the macro and you can develop the visualize the losses. And in case you do not have the geometry in CAD and you just have the dimensions, we have a macro to set up the dimensions as well. So all this is possible. You can even create windings automatically in 2D. So these are all macros that are already available. So now I'm going to jump into optimization of the model in Flux and how you can go ahead and optimize these things. So HyperStudy is the tool which we use for optimization. So instead of you parametrically entering the values and solving it and then you yourself visualizing it, HyperStudy is a tool which couples with Flux and will run a set of experiments. So based on what sort of approach you are giving, it will run a set of experiments and it will give you the most optimal solution. So for example, if you want to minimize the cognitive torque of a motor or improve the efficiency of a transformer or reduce the losses in a transformer, you can take the different things. So DOE is design of experiments, where you can screen if you want to screen, or if you want to check the filling or all those things, you can definitely do it. Fit is when you want to fit your design into some sort of design constraint you have. Something, so say for example, your motor's magnets are at 45 degree, but you want it to be below 30 degrees. So you have the flexibility from 0 to 30 degree, but you want the same performance as you would at 45 degree. So HyperStudy would run it for every step between 0 to 30 degree and tell you at which point in the angle would be appropriate. Optimization for if you can give the upper and lower limit for different design constraints, and you want to visualize some output quantity, maybe the phase error or the efficiency or any of those quantities, you can optimize these quantities for that. And stochastic is where you want to change the inputs and see what would be effective on the what would be the effect in their output. This is what our optimization tool is. So like I was saying before, the bus bar configuration is very, very important. So as you can see here, the initial configuration was as such on the left hand side, very classical configuration, nothing special, nothing different about it. But the losses were somewhere around 602.8 watts in this region, in this configuration itself. By using HyperStudy and setting the boundary limits of the design, we were able to understand the you are able to reduce the what do you say losses to 424.2 watts in DCS 373 watts, with a gain of around 30%. So this is something that a design engineer would not consider unless he or she has some prior experience in the field. This is like this configuration does look a bit off because you can see the faces are not placed in a random order, but this is the most appropriate, like this is the most optimal configuration that can be achieved because the net distance between faces was appropriate and maximum in this example. So this again, this can be done with hyperstudy, and with hyperstudy and flux, coupling with flux, and you can find out the optimum distance. So as you can see, the reduction of inductance loops, the proximity effects have all been reduced, by a great extent. There's another example of optimization where you're optimizing the tank around the transformer. So the initial design, we are given the design constraints, the thickness of the tank, the width on the x-axis and the width on the y-axis, and the chamfer on the corner. So as you can see, the initial design was a fairly convectional, design where you have a square with a chamfered corner, but there was a good amount of losses that were occurring, 96.315 watts of losses with a higher what do you say surface area interaction. So there was a good chance that the integrity of the transformer is limited. Then the best compromise, as you can see here, this solution was developed by Hyperstudy itself, where you gave the constraints of what are the design constraints you have, and then you can reduce the loss in this thing, and at the same time the mu r, basically the relative permeability of the transformer and the magnetic effect on the components kept outside the transformer was reduced drastically. There's another example of a generator. Now let's quickly look at some generator, because when they are very important concepts that have to be simulated because they're the first component and the most important component in which conversion occurs. So you can definitely simulate these generators in 2D or 3D. And although I'm showcasing, the motor characteristics, they also apply to generator characteristics, simply because demagnetization is a very real possibility that can occur. And if you have a field that is being inputted as a PWM field that is being given to this thing, that also can have a great impact on your generator. So different tests that you would want to prefer, if you are coupling your generator in series with some other generators, there will be a certain brief amount of time that it can go into motoring mode and all these things. So simulating all these things are very, very important and something that people usually consider most of the times. Like I said before, Flux has no size constraints. You can simulate any size, device of any size from the beginning of from a small 5 mm motor. I mean, sorry, 5 basically a 50 mm motor, something as big as this, as a 50 MVA motor, as you can see here with multiple coils. This can be seen, electrical excitation is being applied here, and you can see the reaction of the same. Wind turbines, yes, definitely. They are huge, in fact, and they have faces that are very widely distributed along this thing. So as you can see, some of the biggest wind turbines, are almost as big as an airplane. In the coming slides, I will show you. And it's important that they are reliable. They have to be installed, they have to be easy to install, and easy is a very strange term for installing a wind turbine, but definitely they have to be not a challenge to install. And they have to have they have to conform to so many strict rules if you want to connect it to the grid and all of those things. Yeah, today's we have up to 8 megawatts of power being generated from a single wind turbine, and there are different technologies that people use. So DFIGs is something that is being extensively researched for wind turbines, but because of the requirement of an input source, it's still taking some time to catch up with. An example of a large wind generator. So as you can see, we have three. Okay, this is one. So there are so many poles that are being formed in and this is a 12 pole machine. You can see there are 24 individual poles, but 12 pole pairs in the north and south are 12 pole pairs. It's a very huge machine that has to be simulated. This can definitely be not only simulated but also very well understood, because if they do not align, there is a good chance that the speed might not be as per required, because it's wind. It's the most unpredictable phenomenon there is. So the forces that it can handle, all these things are very important. Like I said before, you can see the size increment in the past. From 1980s, we had a 50 kilowatt wind generator, but today we have diameters bigger than a Boeing 747. So there are huge applications, there are huge motors, and it's growing, it's increasing. The size and the capabilities of the human race is just increasing every day. An example, basic size comparison for the motors. As you can see, the 10 kilowatt motor is you can, it's smaller than the human, but the 10 megawatt is like something so huge. Manufacturing might be it's a headache. Of the smallest sorts, but all these have to be simulated, understood, because there are so many regions and so many these things that you want to visualize. And electromagnetic quantities are something that you cannot physically see, but exists. There's another concept, magnetic gears, that is being put into place. So, magnetic gears is something that work just like normal gears, but just because they have forces between them, the wear and tear is very minimal. Um, this is a very interesting concept. This also can be simulated in flux. You can definitely, have a magnetic planetary gear system for a wind generator or anything of that sort, so that you have maximum transmission efficiency. Another example. So there are different faults that can occur, in different sorts of generators, simply because they are coupled to a mechanical source, and mechanical sources are never, constant, or how you would say, uniform. So there are some major mechanical faults that can occur, eccentricity being one of the most important mechanical faults. So you might have one phase voltage shooting way over the other, simply because the air gap in that region is lesser. So that is a definite possibility, and there can be structural failures, such as bearing failures or housing failures, armature and stator faults, in case your field winding is pushing too much current or voltage. Because of eccentricity faults, the insulation can break down. The rotor bar or end ring can have a breakage or a fault if the force is too much. Eccentricity related faults and short circuit and demagnetization, all these are very realistic things that occur on a day-to-day basis in generators. So simulating them, seeing the response, is also equally important. Then you can see, different output differences. So the torque pulsations, average torque will be different. I mean, will be reduced. The generated field will be bad. The voltage will be horrible. So it might even cause like system grid failure to a very great extent. So yeah, Flux allows for monitoring these conditions and even understanding, what are these conditions that throw things to a fail. It's something that I wanted to bring to your attention. So the Three Gorges Dam, it's one of the world's largest dams. It's in China, and you can see how big the dimension is. I mean, the simple this thing is, and you can see the line voltage starts off at 20,000 volts, and the rated output is around 777,000 kilowatt amperes. So it's a huge setup for with this thing, but it is conforming to the increasing demands of China, as their major manufacturer. Power is a big resource that they rely on extensively. So they have pulled off one of the biggest dams with around 28 turbines. So it's a huge this thing. And the fun thing is the no load excitation is around 2,304 amps. So it's a huge amount of current that they require for no load excitation. So yeah, this is another example that with that much current, definitely there will be some effects on the turbine itself and even the components that it interacts with outside. So it's a big it's like a huge simulation. It's like a huge problem if you do not visualize all these results, because minute currents and minute faults and minute things which we overlooked in small size dams and all of that are majorly amplified in such big constructions. This is the same thing. This is the same example of how the turbine looked and how the this thing and all of that looked. So this is a typical generator design workflow. So you'll start off with Compose, where you do a good. So Compose is another tool within Altair. It works on OML, or online markup language, where you're doing some scientific computations, and then you will do a system level simulation to understand what sort of torque input you can visualize on the. So usually mechanical torques, like I said, which are being applied to generators, are not constant or uniform. So you can expect some sort of this thing. So you can simulate that in Activate, which is the Simulink equivalent, or a 1D simulator. And then you can couple it with Flux Motor or Flux 2D, and then go ahead with that's when we start when Flux 2D is when we start with CAE, or computer aided engineering, where we are doing finite element analysis of these models, see their reactions, their magnetothermal interactions, and the different forces acting on them, and optimizing then comes as a part of CAE. So computer aided engineering, you start off with optimizing as the last step, like I said before. After you fix your project and you see that your application is met with, you have a base project to build your optimization on. That's how you get to go ahead with it. But as you step from per step, I mean step by step, the complexity is increasing, the accuracy is increasing. You are getting more real world values, and at one point you will be very close to the actual system that you are going to be throwing into the picture. Let's move into current sensors very quickly. So there are different types of current sensors, like there are different technologies that are being used: shunt, current transformers, Rogowski coils, Hall effect sensors, magnetoresistance, and even a flux gate, which is a very new concept that is being used um, in simulating these things. So current sensors are rarely isolated, in the sense that they will be under the influence of surrounding, what do you say, faces and face wires. So you can even visualize them. You can use them for the security, and for the entire system. The current sensors are expected to be reliable. You need to understand they are the safety device. They're basically the security guard of your building. They have to have even though they're more or less overlooked and not given much thought about, they speak about the entire system. They speak about the entire security of the system. So it's important they have a well above and beyond sensing a range, beyond the limits of the transmission line that they're sensing, or whatever quantity that they're sensing, because fault conditions can throw this for a toss, and they should not be damaged and all of those things. So when if a fault occurs, so it needs to be simulated and understood. So I'll just quickly run over through some values. So as you can see here, this is the current that is being pushed through one of the conductors, and you can see the current that is developed in the current sensor. This is because of the air gap. So in the Hall effect sensor, if you are using, you can check the air gap effect by pumping current into this thing. Again, one face is excited, the face in the center is excited, and the magnetic flux density of the sensor is computed. And this is when all three are given, an input waveform. So there will be a phase difference, or a change in phase from between the different phases. You can definitely, we have an example in this thing as well. You can create a compensation coil for correcting the phase error. Jumping into actuators. So actuators are, again, like if like they control all the things that you wish to control, and all the so this is a motor starter example from Schneider on the upper right corner here. This is a motor starter, and this is a Thomson actuator. Sorry, this is a Thomson actuator. So these can also be simulated, and they have different applications, but at the same time, their reaction time and their inputs speak about the safety requirements of the grid. So the actuator is like, if the system cannot handle it, and the system can handle it for 2 seconds, the actuator has to do it in under 50 milliseconds. So there is a huge requirement in understanding, in having very efficient, very quick actuators. So these are some examples of the results that you can visualize in the actuator. So you know what sort of material. So just quickly run over through a Thomson actuator, Thomson effect actuator. So this is a mobile part. The gray part is in aluminum, and what do you say? The bottom part, the golden part, is in copper. And there's a coil in the bottom part. So the coil, and so they're taken as solid conductors, because eddy current is what these things work on. So they look together when placed together, and this is the electrical circuit. So if you, because you have different coils, right? Each coil is individually modeled, and there's an inductance and a resistance and a capacitance that is being pushed through this region. Then you definitely give the movement of the mobile parts to see the current density. So this is the current density, I mean, sorry, the magnetic flux density, the distribution of the same, to see if there is any saturation points in your geometry. This is the current density. So as you can see, the current density and the effect on the actuator, you can visualize where maximum current density occurs. So you can see it's 3 amps per meter square, in as the highest peak value, and you can see it's reforming, and all of these things can be visualized accurately. This is the current in the coil with respect to time, the increase in the current. So you can see it's gone up to 7,500 amps at 100 microseconds. So it's a very big value. But yes, this thing should be able to handle it. The position, so there's a minimum position and the maximum position. So from the maximum position to minimum position, it took around 420, let's say, so 20, 440 microseconds. These are the joule losses in the entire domain of the Thomson actuator. And yeah, that's regarding the actuators and sensors as well. So I believe I've compared all the bus bars and actuators and generators of the smart grid, of the power grid equipment. Speaking about flux, like I said, these are what sets flux apart from all the other softwares that are out there. So there are quite a few there are quite a few electromagnetic solvers, but flux has a fast and accurate solver, and we have a powerful mesh control which no other software is giving today, and we have efficient modeling of complex situations. So like I said, inrush current and all of that, if you have all the values, flux definitely gives very accurate values. We can import any form of CAD, we can couple with any system level simulation tool, and we also have some of the best multiphysics analysis tools like OptiStruct and AccuSolve. Fully parameterized models, you can parameterize the embedded entire model. Optimization can be easily done at the click of a button, and you can also adjust to the user needs. And we have, like I said, we have different APIs. If you're good at Python or Java or VBS scripting, you can directly use an API and go ahead with automating your entire process. I'll just quickly show you a video from Altair regarding Yeah, so this is just to highlight, this is a resource library. You can scan the QR code or visit altairuniversity.com to see all the different softwares we have, including Flux, and get some basic student licenses to have your hands on with the software as well. I'd be happy to answer any questions if there are any.
Yes, participants. Any question that you would like to throw to Mr. Diol? Because as he has explained so well and so interestingly, from the smallest component, modeling of the smallest component like resistor, inductor, and capacitor, to a more complex structures like wind turbines and the other things. So if you have any question, you can raise the question. He has covered almost all the aspects and the features that the Flux is offering without, I think, skipping of any of the small feature. So those who are interested in working in this Flux particularly, this for prototype development, for simulation, for testing of developed prototype or the product, then it could be a very useful tool, I think. Anybody from the participants? Those who might have worked, who might have come across this Flux software before, and they might have faced some problems, so they can also uh, uh, clarify that doubt, or even at least get the detail of the technical personnel who can assist somebody who's the students might be working in this particular area of finite element method also. Yes, if there is no question from the participant side, we can wind this session up.
Yeah.
uh, Mr. Deol,
Yes, sir. Thank you.
yes, thank you very much for your time and a very interesting kind of the presentation that you have on
Thank,
behalf of your alter.
thank you, sir. Thank you. Thank you
And
so much for the opportunity for presenting.
yes, definitely, and you have touched so many aspects that is beyond, in fact, I should say that beyond the expectation of, as far as myself personally is concerned. So you have touched upon so many aspects, and how the other research area can be even opened up in this particular field.
Yeah,
I mean,
definitely.
designing, it's not only for the designing of the small coils, but it is for designing and developing of any of the components that may not be directly related with the power system or the microgrid. But as we can see nowadays, most of the things are on a scaled, differently scaled basis. If we talk about the microgrid, then the fundamental remains same, and our main objective is to improve, enhance the efficiency of a smaller system rather than the larger system. So in that case, it would be very useful, this kind of tool.
Yes, yes, definitely.
I guess if and I hope that most of the participants will agree with me. So thank you very much, Mr. Deol. It was a very nice session, conducted very well, so well presented. Thank you very much,
Thank you, sir. Thank you so much.
Alter as well as Mr. Deol.
Thank
Thank
you.
you very much.
Thank you, sir. Thank you. Okay, I will be leaving this meeting now.
Yeah, sure. Thank you very much once again. All the participants, now the next session will start at 11:45, and that will be conducted on AC microgrids, islanded operation of microgrid and their optimal control by Dr. Trapti Jain, IIT Roorkee, IIT Indore. And then after the third session, today's third session will be conducted by Dr. Premalata Jaina, IIT Roorkee, on introduction to smart grid technology. So I request all the participants to be on time and join at 11:45, sharply at 11:45. Okay, and you must be familiar with the rules of the ATAL, that at least you should have 80% of the attendance, and on the last day we'll be having a test. So in that you have to secure at least 60% of the marks to get the certificate. So I request all the participants to attend all the sessions, I mean, present be present in all the sessions, involve all the sessions, make the sessions interactive with the speaker, whosoever is the speaker, so that not only gives some fruitful output, but that also improves, enhances our skill. Basically, it is a faculty development program, so that that the information which you will be getting, that could be percolated, conveyed to your students. So that is my humble request, that all the participants should remain present on time during entire session, and seriously attend this program. Okay, so we'll restart the session at 11:45 by Dr. Trapti Jain. Okay, thank you.